Bem-vindos to one more episode of the Type Theory for All podcast. As always, this is your host Pedro Abreu, and I will keep this introduction simple because we will be talking about a very simple type theory. In this episode, I have a nice conversation with Chris Jenkins to talk about the Cedille theorem prover, based on a very concise theorem prover called CDLE. I would say that the main selling point of Cedille is that the theory is so small that the typing rules fit in one single page, and yet it is strong enough to do relevant theorem proving. This is probably the most technical episode so far. I hope you guys enjoy. Let's get into it! Ladies and gentlemen, today I have with me a fourth-year PhD student in the University of Iowa. He's advised by Dr. Aaron Stump and is currently working in the development of the theorem prover, Cedille. A personal friend of mine who attended the Midland Summer School with me 2 weeks ago. With no further ado, Chris Jenkins! Please tell me you got that reference, dude.
Yes, and thank you.
Every single time I listen to your name, that's what I think.
Well, thank you for having me and introducing me with a quite exciting, introduction.
Right. So for the listeners who doesn't know and never played World of Warcraft in their lives, this is a huge meme in the World of Warcraft lore. I'm gonna leave the link in the description. You just watch it, and it's super fun. I hear you actually D&D master, right? So like I thought you would get this reference. So I prepared.
Yeah, I've never actually played World of Warcraft, but yes, it's all right. But yes, I have Dungeon Master before, so
yeah,
pretty nerdy.
Yeah, I tried playing some D&D in the past, but I don't know. I just couldn't vibe with the group, and it didn't pan out. It's a big thing, right?
Yep, you got to make sure you've got a group of players that you have fun playing with. That's for sure.
So, I didn't get a chance to ask you this, but what did you think of the summer school? Oh, yeah, so for the listener who doesn't know, the Midland Summer School is a summer school that happened completely remotely. It happens in Birmingham, and it covers type theory, proof theory, what else? Some, things related to those topics, right? What did you think about it?
Yeah, it was fun. I don't know if you know, but I have a bit of something of a horror story, which I guess I'll share for the benefit of the audience. Not that bad, more funny than anything. But overall, I did enjoy it. Of course, the time zone is a bit off, so
yeah,
I couldn't attend some of the earlier lectures that I wanted to see. But I did get to attend the Isabel Hall one, which was a lot of fun, and also get a chance to talk to the people there and some of the other researchers and meet new people. So aside from missing, the early lectures, live anyway, they do have recordings. It was a lot of fun. The story, basically, this is like a horror story just in general for virtual conferences, especially ones run by Zoom, is that my client was acting buggy. And when they did the virtual conference dinner, where they have everyone in the main room and then they assign you to a random room with 5 or 6 different people. And when they did, my audio started, my audio stopped working. So I had to quit and rejoin. And then I didn't get back into the room that I was originally assigned. So I had to wait for everyone to come back. And then when they did it again, my client crashed. And when I rejoined, there were 2 of me. One me that was frozen in the middle of laughing at something that Thorsten was doing that was kind of funny, and the other me that had just rejoined. And the conference organizer, they thought that the way to solve this was to just kick out the other me, right? And then assign me to a room again. But as I was getting reassigned, Zoom was like, "You've been banned from the conference, so goodbye."
Ooh, so you could not join anymore.
I could not join, and I tried to message someone on the unofficial Slack to get in, and I emailed the conference organizers, and they did change the setting, but unfortunately, it doesn't take effect unless you close and restart the Zoom session. So I missed out on the entire conference dinner, virtual dinner. The only silver lining of that is that apparently I became a little bit infamous. So So I guess that means that, like, I wanted to meet some of the researchers there, and they had, they knew about this incident, so now I've got a higher chance of being remembered by them, just because I was the unlucky person who got.
Hey, talk good or bad about me. Just talk about me, and that's fame, man. I would take it any day. There you go.
Yeah.
So, what did you think about Isabel? Did you have any knowledge about it before?
I did not, and most of the sessions were really about the theory of these inductive and co-inductive definitions. So there was only like a little bit of Isabel. From what I saw, it did seem really interesting, but I'd have to go look at the recordings of the interactive sections, the exercise sessions, to get a better feel for Isabel itself.
Right. So yeah, you work a lot on inductive definitions and whatnot. Did you learn anything new? Like, what was the big thing there? I'm actually envious because I didn't know they would go, like into the theory there, because I also have research interest in those topics.
Yeah, I did. I ultimately found it to be more of a reinforcement of some of the stuff I had already absorbed. Basically, it was looking at things from the point of view of order theory and Kleene fixed point theorem,
Right.
and dualizing that to co-inductive types. So I did get a little bit. I get to learn a little bit about like the friendliness. So Isabel, for co-inductive types, has this like notion of being a function being friendly for co-recursive calls, and I got to talk to a lecturer a little bit about that, because there's a similarity between that and some of the type-based termination stuff that my group is working on.
Well, since we're moving in that path, let's start by what is Cedille, man? Let's talk about Cedille.
Yeah. So Cedille is an interactive theorem prover / dependently typed functional programming language. It's quite different from some of the other languages in that class that probably your listeners are more familiar with, such as Agda, Coq, Idris. So basically, I'll say like what the philosophy of Cedille is. The goal of Cedille is to, or rather, more specifically, the goal of Cedille's kernel logic, which is called the calculus of dependent lambda eliminations. It's trying to be a very small logical base that's suitable for programming with and proving with inductive types and dependent types. And the way that I'll say a little bit about why that's important, but the way that it achieves this mostly is by not having inductive data types as part of the core theory. Instead, they're derivable by using a technique called lambda encodings, which goes back, of course, to the lambda calculus and Alonzo Church. So, what's this about, like having a small kernel theory versus inductive data types in the theory? Well, these inductive type definitions are, formally speaking, they're quite heavyweight constructs to add to your language. You are specifying this schema that describes the class of definitions that the user is allowed to add. Then you also have to include positivity checking in these for the most part. So your positivity checker now has to be part of your core theory. And then you could just stop there if you generate eliminators for the data type, which is basically like a low-level way of using recursive, writing recursive functions over the data types. But mostly what you want is to have some sort of like general purpose termination checker, or that seems to be the way most implementations go. So if you've got general purpose recursive definitions, you also have to have some sort of termination checker in your theory as well. So that increases the formal complexity of your core theory. And what you want, on the other hand, what you want is to have as small a core theory as possible, because, one, you want to make sure that your implementation of it is correct. So in particular, that could be in like a formal verification of the software artifact that's checking this internal theory.
Right. So being small, it's a lot easier to have a small program, and it's a lot easier to check that. Yeah.
Yeah. Or, if you, even so, formal verification could be quite ambitious. So like another advantage is that you can have multiple implementations of that core theory, in the same way that you have like multiple implementations of SSL, right? And then if you're not sure whether or not the proof generated by your, say Cedille is good, well, the internal checker for Cedille might say okay, but you maybe send it over to someone else's implementation to get a consensus.
There's also something called, I think, the Brown.
The Brown criterion, yes.
Yeah, the Brown criterion. So this is like, so the Brown criteria talks about having a small core to type check your language, right? And what you're saying is it goes even beyond this, the Brown criteria, which is not only a small core, but a small soundness proof and sound, all of that, right?
No, not quite. It is just the de Bruijn criterion.
Yeah.
So
Okay.
yeah,
Sounded
like
even stronger in a sense. Yeah.
well, but we it does turn out that Cedille's the meta theory of Cedille is pretty simple. At least if you're familiar with realizability semantics. But that's not really as far as having a trusted computing base, right? What you really
Right.
want to know is that the formalism is small and it's the implementation of it is small. Yeah. A side benefit though of this that we've sort of been playing around with is that since we don't fix the notion of inductive, what is an inductive type in the theory, we've been actually free to explore different representations of data types as imperative encodings, as lambda encodings. So that's led to some really cool results, such as we have a submission going out just now on constructor subtyping, which is basically like say I have the integers data type and I want to extend it to the natural numbers data type and I want to extend it to the integers type by adding another constructor. Well, that is derivable within Cedille. We have promising results on definable quotient types in Cedille, as well as this is still in its early stages, but inductive types and also novel recursion schemes for type
What is that?
extermination.
What is inductive types?
Yeah, so that's a more exotic kind of inductive definition, and I'm definitely not an expert in it, by any means. So I'll just give you the bullet summary, which is that it's a kind of mutual definition of two inductive types, but it's not just that one can reference the other while you're defining it. It's that one can reference the constructors of another.
Oh wow! Okay.
While you're defining it, yeah. So it's a very powerful form of definition, and we do have a in the works. We still need to show examples and write a paper and everything, but we do have a lambda encoding that allows you to do this.
Right. So basically, what you're saying is that the main reason why the Cedille can have such a small core is because you don't have inductive definitions built in your language, and therefore that simplifies things by a lot, right? So
right.
How did you guys achieve this? Why don't what's the novelty here that allowed you to derive these inductive data types that it seems to me that it was not possible before?
Right, yes. So there's I think in the early 90s, there's a paper by Clavers, and sorry if I mispronounced that, that shows that, so CDLE, the core theory of Cedille, is based on, it has as a subsystem a type theory called the calculus of constructions, which is also, the calculus of constructions is also the subsystem of the calculus of inductive constructions, which is the basis of the Koch theorem prover. So this paper by Clavers showed that induction is not derivable for natural numbers in, and presumably for other data types in the calculus of constructions. So that just means that there are other models. There are other models of this theory where induction doesn't hold. And so what Cedille has done basically is instead of just adding inductive data types to the theory, we tried to find some smaller typing constructs that would rule out those bad models, basically. And those typing constructs are basically implicit products, so quantifying over functions that have erased arguments, dependent intersections, which are more of an exotic, quite an exotic feature, and then a primitive notion of equality that is, that's the heart of basically, the rules around the equality are basically the window into the model of Cedille, as that's how I see it anyway.
Right. And also, usually the calculus of constructor is also intrinsic type.
It can be.
Right.
It can be either way. I mean,
Yeah.
So yes, you can have the Curry style or Church style. I think this is one of the topics that you wanted to get to. Version of the calculus of constructions. So the difference, of course, good to talk about this here. the intrinsically typed or church style calculus of constructions, or just any intrinsically typed theory. What makes it intrinsically typed is that types are part of the programs, right? So you could have two programs, two functions that look exactly the same and compute exactly the same way, except that they have different annotations on them. So they wouldn't be the same thing, because the notion of type is tightly tied to the notion of program. In a Curry style theory, you make a philosophical choice that programs and functions, computations come first, right? So you really just care about an untyped language, and then you're working in an external system that's assigning types to these terms. So that means, for example, that intersection types only make sense in Curry style theories, because there's no way that you could say that a term has two different types, unless those two types are convertible. Basically, unless those two types are exactly the same thing in a intrinsically typed language.
So Cedille wouldn't even be possible in an intrinsic type, because you wouldn't be able to have the dependent intersections, right?
Right.
Could you be able to have this intrinsic notion of, how did you call it, the equality constructor?
No, the equality also is the equality. It's not the equality type is not even heterogeneously typed. It is untyped. So this is making a very very strong, or staking a very strong position that when you're talking about terms in Cedille, you're really talking about untyped terms.
So basically, what this equality does is really look into the structure of your term, like goes deep into how your function actually structurally looks to the other. Is that correct?
Yes.
So it must really be the same structure, like each lambda and even the name, maybe.
No, not the same name. I mean, we are, of course, alpha. Programs are equated up to alpha conversion. But it means that, yes, the two programs have to be, after you remove all of the typing annotations and erase arguments that don't have anything to do with computation, two closed terms are equal if they are, the same lambda terms up to, beta conversion.
Right. And you said that this notion of equality is what gives you this window inside the model of the theory. What do you mean by that?
So the types in Cedille are quite directly interpreted as sets of beta-eta equivalence classes of terms. So when you have an equality that term T1 is equal to term T2, that is directly translated to this beta-eta equivalence class of an untyped term is equal to this other beta-eta equivalence class. So they're in the same. These two terms are in the same class.
What does it have to do with like a modeling?
That's the model. So you've got you've got the theory, which is the formalism, and then you want to prove, say, logical soundness, right? So Cedille gives you certain has certain meta theory guarantees for the programs that you write in it, and one of these is that there's no proof of false, right? Where false here is the function, the polymorphic function, for all x, x. So stating that every type is provable, right? So how can you prove that there is, no proof of false, right? Well, you can give a model and then show that the theory is sound with respect to the model. And then if you show, if for all x, x is interpreted as the empty set, right? And your interpretation is sound, then you know that there can be no close proof of for all XX, because
Gotcha.
Yeah.
Right. That's really cool. Since now inductive data types is not part of your language, so how do you come with their derivations then? What's the trick?
Oh, so I will say that the surface language Cedille does now have we have the convenient inductive data type declarations. And,
right, but under the hood, you're
under the
actually
hood,
converting this to something else, right?
Right. They're being translated to Lambda encodings in the core theory.
Okay.
So as far as the process is concerned, I don't want to get too in the weeds because it's a little bit hard to.
Really deep. Yeah.
I don't want to convey. I don't. It's hard to convey this vocally. I will shamelessly self-plug and say that I've made a few videos on the YouTube channel called the Cedille Cast. And
I actually had plans to talk about that in the introduction, but I forgot. I am very sorry, but check out his YouTube channel, and it's on the description of our podcast. Check it out.
Yeah. Well, the group's YouTube channel, but I do think I'm the most prolific contributor.
You're the pretty face of Cedille, Chris.
Yeah, I suppose so. Anyway, the to give like a high level, just a really high level view of how the derivation goes is you pick an encoding that you want to work with. So for simplicity, we'll just say that church encoding. You can define that in just regular old polymorphic lambda calculus, and then you also there is a related inductivity predicate for church encodings that you can express in dependent types. You can express this in the calculus of constructions. So for like church encodings, this would be like for all properties P over church encodings, if P holds for church encoded 0, and for all M, if P holds for M, then P holds for the encoding of successor of M, then P holds for some particular number, right? So we're not talking about induction and saying that this shows that P holds for all of the numbers. You're talking about a predicate that says given some particular N, right? If I show these base and step cases, then I've shown it holds for this N, right? And then this is the next part is where dependent intersections come in. There's this really, amazing correspondence that is originally due, I think, to Levant, that if you take a data type, if you take a particular element of a data type and you prove that it satisfies this predicate that I've just described, that proof is isomorphic to the church encoding of that data type. So the proof say that that the induction principle is proven for 0, right? You say give me a proof that P holds for 0, give me a proof that it holds for the in a successor case. That's lambda z, lambda s, and when you do, you return z, right? That's church encoded 0, and the same thing for a successor. So what Cedille does is says, well, we're gonna pull a magic trick. We don't actually have the data type. We just have these church encodings. So we're gonna give proofs that church encoded 0 satisfies this inductivity predicate, and that church encoded successor preserves this inductivity predicate. And those two proofs are not only are they isomorphic to 0 and successor, but in Cedille they are actually the same term, just with different type annotations.
Wow.
So then you put them together with dependent intersection, which is a way I should say, like, so intersection types allow you to assign two types to a single term. Dependent intersections allow one of these types to talk about that very term at the other type. So in this case, we're saying that 0 has the intersection type that is 1, it's 1, a church encoding, and 2, a proof that 0 as a church encoding satisfies the inductivity predicate. And then there's usually a third step, because now you've defined a new type. So the third step is much more technical, but you're basically bridging the gap between this inductivity predicate for church encodings versus an induction principle for this new type that you defined, and that's usually where the equality type comes in, is to collapse this distinction, because you're really just talking about two different typings for a term.
Wow, that's really amazing. So I think you mentioned at some point something called Scott encodings as well. What is that? What does that? What's the difference between Scott encoding and church encoding? Maybe you want to give like a brief idea of what church encoding is as well.
Yeah, and I don't think I've talked about Scott encodings yet, but I've certainly talked to you in other discussions about them. But yes, yeah. So the sort of like view of lambda encodings in general that I've come to really like is that I don't think this is, you could say this like or I don't think it's true 100%. Like, I think I may know an encoding that this correspondence doesn't hold, but regardless, we're going to put that aside for now. Is that I like to think of Lambda encodings as solutions to structured recursion schemes, right? And to give you an idea, the church encoding is a solution to the iteration scheme. So church encoded naturals are basically, if you're trying to find a solution to the type nat and the constructors 0 and successor, such that you can type the iteration scheme. So with that, then it becomes pretty easy to, if you follow that correspondence, then it becomes pretty easy to describe the Scott encoding because it's a solution to the case distinction scheme. Yeah. So the idea there is like, the big difference at a more low level, the big difference between the church encoding and the Scott encoding is that, when you're defining a recursive function with a church encoding, you have access to the previously recursively computed result, but not the predecessor, right? The predecessor is sort of consumed already in making that recursive call. Whereas with the Scott encoding, you do get the predecessor, directly, just like with case distinction. But there's not an obvious way to do recursion, right? You're not handed a previously recursively computed result that you can then refine. You just handed the predecessor. So it might think that, okay, well, with the Scott encoding, it's really easy to compute the predecessor, where it's actually sort of a famous result for the church encoding that there's no efficient predecessor function for church naturals. So the best predecessor that you can get takes linear time, which is pretty terrible if you're like, I just want to get the next number, right? I shouldn't have to traverse the entire size of the number. I shouldn't have to go down 100 steps just to get to 99. That should be a constant time operation. But you don't get that for the church encoding, and you do get that for the Scott encoding. So sort of my special interest in Scott encodings, I guess, is that when I say it's not obvious how to define recursive functions over them, when you don't have already a general form of recursion, like general fixed points or general recursive types, but you still can actually still define a strongly normalizing recursor for Scott encodings in certain type theories, certain somewhat exotic type theories. And to give you an idea, the setting that I learned about this in was another Curry style type theory that had cyclic subtyping rules, which is, cyclic proof theory is a really deep and complicated topic that I've only studied just a little bit, but it's, this is a very sophisticated and cool subtyping system that they've developed. And the only other systems that I know of where you could do this, the only other system that I know of where you can do this in theory is Cedille, which is another very, strange and heterodox type theory.
Wait, so Cedille can actually do cyclic proofs in them?
That's not what I'm claiming. I
Okay.
am sort of interested in pursuing that correspondence a bit further.
Okay.
I'm sorry. What I should say is this system that I'm talking about, Lepik and Rafali, they use cyclic subtyping to type a strongly normalizing recursor for Scott naturals.
Gotcha.
And Cedille uses derived recursive types to do the same thing.
Do they still have soundness guaranteed about their logic then with cyclic proofs?
Yes, because cyclic doesn't mean circular. So it sort of sounds like it would be that it couldn't be consistent, but cyclic proof theory is sort of like how to put it. The basis of it is proof by infinite descent. So and that idea is that you give sort of a cycle in a proof. You give a proof that's a cycle, but every loop in the cycle, some measure is decreasing.
Right.
And then the reason it's sound is because that measure is a natural number, right? And you can't have an infinite descent from that natural number. So at some point it's going to bottom out.
Very interesting. Well, yeah, the way you describe it, it seems that there might be some correlation, between what's happening in the cyclic proofs of their language and Cedille, right? That's actually very exciting. Yeah, maybe you can actually encode the cyclic proofs in Cedille. We just don't know how yet.
Yeah, that is certainly something I'd be interested in looking into. The fact that you can do it for this one example, which is it's quite sophisticated, the construction for the recursor for Scott naturals. The fact that you can do it for a complicated example like that makes me think, well, what else can you do?
So, okay, what's the difference then between how you work in Cedille and how you work, say, in Coq and Agda? Is it kind of similar? Is it too different? How would you compare?
Do you mean like the tooling, or do you mean like how do you go about like the kinds of problems and the ways you approach problems in these two settings?
I think I'm interested in hearing, like, do you guys have any interest in being, like a big theorem prover? What would be the use case? Is there any use case, or is it more interest in seeing what are interesting meta theoretical results that we can derive from here? What are the interesting set of problems that Cedille would make it very easy to work against? Or even, like, maybe because, for example, even the idea behind Idris, I never know how to say Idris or Idris. Anyways, the theorem
I've
prover
heard Idris.
Idris.
Yeah.
The idea is to be, like, not only a theorem prover but a programming language, right? So what's the philosophy behind the Cedille theorem prover?
Yeah. So right now it's more of an exploration tool. We do, of course, we want to forge a new path basically into the design space of dependently typed programming languages. So some of the things that you can do in Cedille are, for example, this was like a ICFP 18 paper. Is you can So one issue with programming with dependent types is this problem of data reuse, right?
Mm-hmm.
And what I mean is that you have like ordinary lists, that you program with, and then if you want to reason about the lengths of those lists, you go to length index list, or what's commonly called vectors, right? Or if you want to talk about provably sorted lists, you come up with another data type that's the type of sorted lists, right? And there's functionality that's shared over all of these variants of lists, right? Say, appending, right? Although it's a little bit different, with sorted lists, you'd have to have an additional proof that the bounds match up. But with length index list, doing append, doing a map, all sorts of things. And if these are two, nominally different types, then you've got two choices. You re-implement all the functionality, for lists over length index lists, or you write a conversion function, right? You can convert back and forth between them. But the conversion function, what is it going to do? It's going to tear down, the length index list, and for every, cons it removes, it's going to replace it with a cons from the other data type. So what you've got is a linear time computation to do basically nothing, right? To just take some data and change its representation so it has the right type. So in Cedille, you can do this conversion in zero cost time, right? It's the retyping function is quite literally lambda xx. I mean, there are more annotations, there's a lot of more fancy annotations going on, but if you take the reuse program and then you extract out the actual computation, it just takes a list and returns a length index list whose length is the length of the original list. So you get this reuse at no runtime cost.
That is really cool. That's really, really cool. Yeah. So what about, the usability of the tool? How would you? I know you guys don't have tactics, for example, right? The same way Agda doesn't. Does Agda have tactics nowadays?
The last I heard, Agda uses reflection. That I think this might be very out of date. So, but the team is going for sort of hygienic tactics where you take a goal state in the language and reflect it into a data structure, and then write an Agda program to manipulate it, and then turn that back into. So I don't know what the status of that is, but there's certainly an interest in tactics, and there's some amount of automation, I think, implemented in Agda, but not yet, I think, to the extent that they have in Clock.
Mm-hmm. And so you don't have tactics at all?
No. So it's it can be, if you're working through, if you're doing something like, say, reasoning about modular arithmetic, which is something that I did have to do on this like definable quotients thing. It can be quite it can be quite a challenge. You have to spell out your proofs pretty explicitly.
True, true. Well, but on the other hand, there is a really, really nice package for Emacs that really helps you to program in Cedille, right? Like, really gives you what are the types being expected and how things match up, and shows even you can even walk through the term and see what are
Right.
the types of the intermediate structures and whatnot. It's a very nice tool, actually. It feels
Yeah,
nice.
yeah. I also agree that reading Cedille programs, if writing Cedille programs is kind of painful sometimes, reading Cedille programs is quite pleasant because of this tool
Right.
that allows you to
Yeah.
basically navigate the abstract syntax tree and inspect things like, what's the type here? What's the current context? What are the unsolved? We have a very limited form of type inference, and that was implemented by me, so I can I can say whatever bad things I want about it. But you can even like look at an application that has that's inferred some type argument, and look at what it look at what the the solutions were for the meta variables. So
right. Yeah, those things are actually pretty cool, and also programming with rows and like this notion of
yes.
refinement. And to be completely honest, when I open up a Cedille script, I'd say it feels nice to look at those. How can I say? It's not. It's a very different programming language because there are not many keywords. Like it's very
Yes.
a lot of symbols, and I mean it can feel very confusing at the beginning, but as you learn, it feels nice because it's very compact as well, and it looks good. It's really nice. I enjoy it.
Glad to hear that. Yeah, I mean, I'm certainly not an unbiased I'm not an unbiased witness at this point, but I do sort of agree that it's a little bit quirky at first, and we've certainly had a number of reviewers complain about not quite understanding the syntax. But after a while you certainly get used to it, and it does to me, I think, make quite a lot of sense.
I was talking to this with someone that had a similar point of view. And I get it. It's kind of annoying, like everyone is using to doing the same thing, and it's a lot easier to move from different programming languages and programming environments. So when someone comes and show different things and new stuff, it's hard, right? Like it's you're adding complexity, and it's harder for people around to understand, and it's a good it's a fair argument, I'd say. But at the same time, for me, there must be people who comes to like try changes. Has to become people who comes and, hey, what if we throw everything away and start from scratch? Like, what if we don't assume anything that we already have? What if we literally try to solve this question here from scratch? And what's gonna happen, right? So that's a very interesting question for me, and a very interesting endeavor. Like, and see what works and what definitely does not work, and maybe there are some of these ideas that we can migrate in between, right? Like, maybe you guys can come up with some really cool ideas that the cog developers are gonna be interested, the agri developers are gonna be interested as well, and that's very good, right? Like, that's why we do different people do different research, and we collaborate with each other. So
sure, absolutely.
it's a nice thing. Yeah,
we do also want to have some of the like right now our the syntax for defining recursive functions is it's quite a bit, I should say, more primitive. And again, I can say that because I'm the one who designed it and implemented it, so I can say whatever bad things I want about it. But the syntax for that is still a little bit low level, and we do want to eventually have the nicer, higher level, like left hand side with patterns equals right hand side, that notation that people are more familiar with in say Pascal Agda.
To be completely honest, though, I believe that there is one thing that you guys got right and that completely sucks in Cog, which is dependent pattern matching. So in dependent pattern match, you usually need to write down the motive, and in order to understand what's happening under the hood in Cog, it's a nightmare. It's a nightmare because all those keywords, as, in, return, blah blah blah, like, those doesn't come together. It's hard to understand what's going on in Coq. So when I actually understood dependent pattern matching was actually when I was learning Cedille. Because you guys provide the right intuition behind what's the motive doing here. I maybe you want to get into the details. What does this mean? Because I'm definitely not going to be able to explain here. But
well, I will say that if you don't know what's going on with dependent pattern matching, it very well is probably easier to work with Cedille because you don't get any of that automation.
Exactly.
So you have to spell out, the equations explicitly for the terms that are revealed by pattern matching. But I would say even despite that, having dependent pattern matching in Cedille is something that I would really, really like to have.
Right. No, yeah. So my point is that the key idea behind dependent pattern match is to write down the elimination function, right? And the way you write down the elimination function in Coq is, I would dare to say it's wonky. Because it doesn't feel like it's a function at all. It's like it feels like it are different things mentioning about different stuff here and there. And as someone who is learning, it felt hard to get a hold of it. But on the philosophy of Cedille, it's just this one function, and you know exactly what is expected, why we're writing this and why we're writing that. And it feels, natural to get the intuition behind what this is doing, this is literally just telling what's going to be the return of my pattern match, in a sense, right?
Mm-hmm.
So anyways, moving on, you mentioned that you would like to touch on the method theoretics guarantees of Cedille. What are the interesting things that you have there?
Yeah, so I did mention one of them. This is the logical consistency, or there's no closed proof of false. Another one that's pretty straightforward is so Cedille is a Curry style theory. So okay, I should back up even further. So one of the things that you would be interested in an intrinsically typed language is something called type preservation. So you take your well-typed program and you run it, and however far you run it, what you get is still a well-typed program, right? Being extrinsically typed, this commitment to untyped terms, like it goes quite deep, and in the sense that there isn't an operational semantics for terms with type annotations. There is just beta reduction of untyped lambda calculus.
You're making it sound that it's really easy to get stuck now.
But how would you get stuck? Because you can't get stuck with untyped. You're not going to get stuck in a sense with untyped lambda calculus terms. There's no stuck state.
Okay, go on.
Yeah. So what you get instead is a semantic type preservation. So if you have a typing derivation in Cedille that says that this term is an element of this type, that means that the beta eta equivalence class that the term represents is in the set denoted by the type, right? And these sets are closed under beta eta reduction. So if you then take that term, that untyped term, and run it, right, sort of like, by definition, I mean, it's not exactly by definition, but pretty much immediately, if you run that term is still going to be in the same equivalence class, so it's in the same set, right? And then the third thing, and this can get a little bit more, this is basically like there are certain trade-offs to using Cedille, and this is one of the ones that may cause people to sort of like pause and like, well, take notice, because you can type non-terminating terms in Cedille. That doesn't impinge on soundness, because you can't take non-termination in Cedille and use it to inhabit any type, right? The terms that are non-terminating, their types will reveal that those types admit non-termination. To make that a little bit more concrete, the termination guarantee in Cedille is dependent upon the type. The termination guarantee for a term depends upon the type that you can assign it. And so in particular, if you can assign a function if you can assign a term a function type, then that term is call by name normalizing. And I should also mention that all data types that we've worked with have that property, that you could take the term for a data type, and you could take a term that's an element of a data type and also assign it a function type.
Right. So this is hard for me to follow. So can you repeat that part where you say that you cannot inhabit a term that is going to be that doesn't terminate, right?
Yeah, you can write non-terminating terms and give them types in Cedille, but the types would not be just ordinary function types. You'd have two cases basically. So the two ways that that non-termination can be introduced in Cedille. One of these is that it's possible to derive just a type for all untyped lambda calculus terms, and so we call that type top. And so of course that means like non-terminating lambda calculus terms have that type, right? But you can't really, like, top is the least informative type that you could give a term. It's just that it is a term, right? It's closed in context. That's basically all you can say about it. So you can't for an arbitrary term of type top, you can't use it as a function and know anything about the result. The other way you can introduce non-termination is by having an inconsistent context. So if you have a function that if you have a function that assumes that true is equal to false, right? That function would be call by name normalizing, which means that if you reduce that function, you'd get to a lambda expression. But at that point, the body, because you don't reduce under lambda abstractions with these call by name, with the call by name operation semantics, or call by value. But in the body, you could use this proof that true is equal to false to do really mischievous stuff. Basically, assign a type to omega, to actually assign a meaningful type to omega, because at that point you've already assumed you're in a world that's inconsistent. And one of the things you can do in Cedille is reason about the types of programs. But closed terms of function types are guaranteed to be call by name normalizing.
Is there a keyword to add axioms in Cedille?
No.
Okay. Yeah, that makes things easier because it's more of a more tight control over the context, right? It's right there written in.
There are ways to simulate adding adding axioms.
Oh yeah?
Yeah, this is one of the axioms for equality that gives you quite a lot of power, is the direct computation rule. So it allows you to say, basically, like, I have a term that's well typed, right? And then I have another term that I make no promises about, except that it's equal to this first well typed term. And that the phi rule allows you to graft the one type to the other type. So you can basically assign you can take an untyped term, and all that you know about it is it's equal to a typed term. And from that, this allows you to assign that type to the untyped term.
How do you go from that to axioms?
Right. So if you want to, you can use holes. So this means that the program won't type check, right?
Oh, right. I see.
So you can use holes to give some like definitions that you don't define, but then you can use phi to specifically say that this expression is equal, that this expression is equal to that expression and it has this type.
Right. But then in the end of the day, you don't. Yeah, the whole is. I would say the whole is the axiom here, because the whole doesn't. Yeah. It's a term that has a type but doesn't have a body, so it can be literally anything. Yeah. Okay. Yeah, I see that. Any other interesting meta theoretic guarantee?
Maybe not so interesting, but I did recently contribute a result to Cedille's meta theory, which is so I mentioned that we don't have the language of terms is really untyped, and so you don't have a notion of type preservation. But the language of types, in Cedille is church style. So kinds are intrinsic parts of types, which kinds are the classifiers for types. And I recently proved that you do have syntactic kind preservation when you normalize types. So
you don't quite have the lambda cube in extrinsic type theory, right?
Yeah, it's a little bit different. I remember reading, the place that the origin of the implicit product, which is one of the type constructs that Cedille adds, is by this researcher called, and again, hope I don't mispronounce his name too terribly, but Michael. And he had proposed a formalism for these kinds of theories that are more, that are more Curry style, and specifically ones that have implicit products as implicit pure type systems. So, but yeah, it is it's not quite. Yeah, if you're query style, then you don't quite fit into the Lambda cube.
Right, but we still can draw some parallel, right?
Right.
Because as I could see, Cedille is not quite far into the spectrum as CIC, because CIC you can have your types talking about literally everything, right? That you can conceive, and it seems to me that Cedille is a little less strong than that, in the sense of like you can only talk about second order, in a sense, second order properties. Does that make sense to you?
Well, I think what you're getting at is that the universe, the universe hierarchy in Cedille is stratified, right? Sorry, I mean not stratified. It's truncated is what I'm looking for. So you have terms, types, and kinds.
Right. Yeah.
Right. And types are essentially simply kinded, although kinds can abstract over terms as well. But
right.
Essentially they're simply kinded.
Exactly, but in COC it's like it's not stratified. You can go all the way down and
yeah, the extended. I think this is like the extended calculus of constructions. Because I think the original formulation of calculus of inductive constructions doesn't have a universe hierarchy, but as it is implemented in Clock, you've got this. Yeah. You've got this hierarchy where you can talk about types at level L can talk about types at level L minus 1.
Right, yeah. So yeah, basically, yeah. What I was looking for is that in Cedille you stop at kinds, because then when you're talking about kinds, you cannot go down anymore. Like that's it.
Right.
That's it. You define your type and you can give a shape to your type, and that's it. Right.
So does this mean maybe this is something I don't think I mentioned in the prep notes, but that might be interesting to talk about, is that type level programming in Cedille is more. This is one of the disadvantages of a query style setting, is that it seems to me that type level programming is a little bit less. I mean, the things that you can do with types are not as sophisticated as what you can do in an intrinsically typed language like Agda. For example, I want to have in Agda, I have no problem with having a large pair, right? A dependent pair where the first element is a type and the second element is a term of that type. What can I do with that pair? I can take the first projection. I can project out that type. Well, in Cedille, types, again, are not really part of the term language. They're just, annotations on top of terms. So you can define the type of a pair like this in Cedille, but you cannot define a first projection function. Because that type isn't there. There's nothing to project out. So a similar sort of thing is like large eliminations. So taking an inductive type and recursively computing a type from a term of that type is something that is pretty straightforward to do, to formulate and set up in an intrinsically typed language.
It depends. It depends. It's very easy to break your stuff with that. So you have to be in the right universe in order to do that. Otherwise, things can go wrong very fast. But
even in a truncated universe, you can have special elimination rules. One set of rules for small eliminations and one set of rules for large eliminations, right? So you don't even need a universe hierarchy for large eliminations. But that's, especially in Cedille, data types are not primitive, so you don't have special small elimination rules for data types, let alone large eliminations rules, right? But something that I and a couple of my colleagues have submitted recently that we hope to get some feedback on and maybe even publish is a way of simulating large eliminations. But yeah, by using type coercions instead of actual computation at the type level. So that's exciting work that we're doing.
And finally, I think the last topic we wanted to cover is type-based termination checker. What is that?
Checking, yeah. So I mentioned at the sort of the outset is like why what is Cedille and why should you be interested in it, is that one of the ways that complexity can be introduced into an interactive theorem prover is if the core theory, or even if the core theory, for example, has general fixed points for recursive functions, because then you need to make sure, if you want your theory to be sound, you want to make sure that your recursive calls are well-founded. So there are a couple of different ways that you can go about doing this. You can just forget these general, fixed point definitions and just work with data type eliminators. But that's a little bit low level. It's not really convenient to work with. So that's why most, interactive theorem provers that you use have something that looks like general recursion, except, it isn't fully general recursion. So languages, like Agda or Coq, they use syntactic termination checkers that just make sure that the function, the recursive function that you're defining, when you call it, it's being called literally on something that was revealed by pattern matching, right? Or it could be more exotic and be revealed by nested pattern matching. But that's essentially the idea, is a syntactic check. These syntactic checkers they can be a bit brittle. I mean, if you just take that recursive call and refactor it, using a higher order function or whatever, then suddenly the function that you've written doesn't pass the syntactic check because you've refactored the direct application. So syntactic termination checkers are great, until they stop working, and then you realize that the reasoning that's involved, it's not compositional, because it breaks with refactoring, and it's not local, right? So that's why a lot of researchers are now interested in type-based termination checking, where you have the types, basically you extend the type language in some way, such that that the types tell you what are legal arguments for a recursive call. And the reason that this is desirable is exactly because reasoning about types is local, unless modulo sort of unification and whatnot, right? If you just if you ignore that bit, but for the most part, it's local and it's compositional. So most familiar example of type-based termination checking that people will have heard of would probably be size types.
Right. That's what I was thinking about. It sounds very similar what we're getting into here.
Right? Yeah, that's probably the that's an excellent example. So you've got data types that now come with size indices, and the function that you're defining recursively, it's only legal to call data, make a recursive call on data that has an index that's smaller than what you started with. So, but this requires an extension. If you just take some calculus of inductive constructions or Martin-Liff type theory, you extend it with size index types in order to get this. So in Cedille, we're again doing something quite different. And what's kind of cool is we're going back to the inspiration for type-based termination checking, which is Mendler-style encodings and Mendler-style recursion schemes. So we don't need to get too much into the weeds of again what this is, but it's another just as a high level, Mendler-style recursion is another kind of structured recursion scheme, but it's neat because it looks a lot like general recursion. And the key idea is that you get the handle, you get your handle for making recursive calls, but the arguments that you can apply it to it's not the data type, it's this abstracted type, right? So really, termination is being guaranteed by polymorphism alone. No addition to the language whatsoever. It's all just based on polymorphic typing, which is something that functional programmers are pretty familiar and comfortable with.
Right. That sounds very powerful.
Yeah. So the simplest formulation of Mendler-style recursion is it doesn't really even compare. It's much weaker than size types. However, something that our group has been working on is taking Mendler-style encodings, which are just how you define data types in Cedille with Mendler-style recursion schemes, is you take the scheme and you turn it into the encoding. But defining an encoding that's powerful enough to be able to talk about taking data and doing multiple levels of case analysis. So you could make a recursive call on predecessors that are arbitrary deep, but also take some data and kick off a subsidiary recursion where you rebuild that data up to a certain size. And again, this is all implicit, right? There's no explicit notion of size here. But it's just like, I'm going to rebuild the data into a certain type that I can then, at the parent recursive function, and it's still legal to make a recursive call on. And it's all just type variables, no indices whatsoever.
When I talk about Cedille, I'm usually talking about the surface language. And you, when you're talking about Cedille, you're probably talking about the core language, right? But in my head, so this probably comes down when you're doing the pattern match. So pattern match in Cedille in the front end, it's basically like the mu, right? It's been a while. I don't play around with Cedille, but my times, like it was the mu.
Yeah, the mu symbol is for kicking off a recursive function over data types. Yeah, and then sigma is what we use for just case analysis.
Yeah. When I first started playing around with Cedille, the mu was for both. It was fine, but it's nice to have one for each. Yeah, I can see the like. Anyways, but yeah, so in this higher level language, so every time you do this recursive call, like you're opening this recursion scope, you're basically like retyping, and then inside this new scope here, then you have this new kind of type that will allow you to do the recursion or not, right? Yeah.
So when you're making a recursive call, you do case analysis, and the subdata that's revealed, the recursive subdata, it doesn't have, like, say, type nat, right? It has, this abstracted type R that's introduced, completely fresh,
right?
To the,
which is coercible back to R to nat if you want. Yeah.
Yes, exactly. So the recursive function that you're defining, the arguments it takes are also not of type nat; they're of this type R. So you can't call it on an arbitrary nat, because that would be unfounded, but you can call it on the subdata that you revealed. And then, you can take that subdata and inspect it further, and that inspection is type preserving. And also, if you want to do something else with that subdata, like kick off some other recursive function that expects a nat, you can you can coerce that type back to the type nat. And again, that coercion is just a retyping function. So what it boils down to is just lambda XX.
Oh, hang on. But if you call another function in your argument here, then you can grow your argument arbitrarily. No?
Right, but you've left the type, right? You went from this type R to type nat.
So you cannot come back. That's the key.
Right. Yeah.
Right. Mm-hmm. You can go from this new type that your recursive function expects back to nat, but not the other way around.
It's a bit like a subtype, right?
Yeah.
You can think of this type R as being the subtype of naturals that are predecessors of the current natural.
Yeah. That's really cool, actually. Yeah, like a notion of subtypes that never talks about subtyping.
Yeah, for termination checking. Yeah, but I mean that's the idea for size types as well. Is that you usually have a notion of promotion in size types, that you can take a term at a certain index and promote it to a larger index, without a problem. It's just going back the other way. That would be unsound.
Right. Wow. Yeah, that's pretty cool. Well, we are already more than 1 hour in this episode, so we should probably start wrapping it up. Is there anything that you think we left out? Would you like to mention, or, an interesting anecdote you would like to share?
No, I think we did a pretty good job of covering quite a lot of bases for, an introduction to Cedille. And I fear that I may have already dived too much into the weeds, but, hopefully I hope your listeners get something out of it. And yeah, I mean, if you want, if you, listener, are interested in learning more about Cedille, we've got a web page. I think it's just like cedille.github.io. And also a GitHub page for the project, and it's open source, so you can take a look at it, and yeah.
It's probably a good time to also mention that your advisor also have a podcast, and they should also check it out. It's the Iowa Type Theory Commute podcast, and it can be really technical over there. Although he is an excellent teacher, like he's an actual professor and will teach you things from bottom to the top, and like
Absolutely.
with an actual yeah in a way that it's understandable. It's a very nice podcast. You guys should check that out. So yeah, thank you so much for coming here, Chris.
Thank you again for having me.
So yep, that was it for this episode. I hope you guys enjoyed it. Don't forget to check out the links in the description. If you guys have any questions or comments, leave them in our website www.typetheoryforall.com, and I'll see you guys next time.